Good afternoon. We start again. We will be doing a very important step now, that is like getting into a little bit of justifying Six Sigma and initiating a Six Sigma mission or a Six Sigma project. How do we do that? Let me start with the slide that I have here. Notice here I have restated the mission of total quality management, which basically is a philosophy that involves everyone in our organization in a continual effort to improve quality and achieve customer satisfaction. That is the stated mission of TQM. And how do I really activate this thing? I have top management direct involvement. That is one of the pillars of TQM. Then we have strong customer orientation, and we have already found out the reasons for this. We have company-wide participation, that also we are pretty clear about. And then, of course, we've got systematic problem solving, and we have continuous improvement as the theme. These are the requirements of TQM. If you're doing these things, you're doing TQM. There's no issue at all. And people would be happy to tell you that you're a Six Sigma company. No problem at all. But how long can you sustain this momentum just by basically saying this is a way of looking at things and so on, you should be customer oriented and so on. And all you're doing is you're trying to propagate a particular philosophy. That's what you're doing, without giving what we say tangible reasons for it, a tangible justification for it. So what is missing here? Missing here is money, and that is the language of business. And most managers will probably say, well, fine, I agree with all that. And in fact, it's just fine, I'm quite used to that and so on. And I know I must have orientation toward customers and so on. But you talk about all the training and so on that I have to go through, I have to put my people through all this. How can I justify that? I do not see an impact on the bottom line. You promised nothing at all. You just asked me to do these things, and you tell me that this is going to be, you must take this on faith, this is going to be good for you. So dollar being missing, dollar is something that is being absent. It becomes very difficult to justify the sustaining of TQM. It does become difficult. Where do I find the justification? The justification I find by going into something called the cost of quality. And then look at the screen here, right in the middle, right in the center, we've got something called cost of quality. Actually, it should be probably reworded. It should be called the cost of poor quality. Let's take a look at what actually is going on here. And the first thing that we see is something called external failure costs. You all know, if I produce something and if it is sold in the marketplace and it has some adverse impact on the user, something happens to the customer because of this. And in a factory, it could be that I supply him bad parts, so his production stops or it becomes defective, or he has to have a lot of rework and so on and so forth. That's an impact. That's an external impact. It's probably a pretty mild external impact. The bigger impact could be that the tires that I supply, they burst on the road and so on. Or the medicines that I supply, they are not packaged properly, so there is some pilferage and people put in some spurious drugs in the same packet. Any of these things can happen, and these are all external failures, and that can be a pretty big cost to the company. That's like one type of cost. And in trying to deliver quality, I have something called appraisal cost, which is the money that I pay the inspectors for buying raw materials, for buying various chemicals and so on, for buying instruments and so on. All these monies, they are being spent to try to keep the inspectors alive and make sure that they are able to make the measurements and produce the data that we need to be able to control the process. Then we've got something called internal failures. What are internal failures? These are the scraps. These are the rework before the product is shipped out. All this is happening. The internal failure costs are being incurred before I'm able to ship the products out. It's very important for us to realize this is also a drain on the company's money. So, in fact, all these three balloons, I have three balloons here. I've got external failure, I have appraisal cost, and I've got internal failure. These are balloons that are basically, they're going to reduce the profit of the company. They're going to raise the expense and they're going to reduce the profit. Now there's one balloon which I've just added here, and these are called preventive costs. It turns out that prevention costs are those things where I try to correct the situation, I try to reduce defect, I try to reduce rework. I try to reduce internal failure. I try to reduce scrap. I try to reduce external failures. When I'm doing these things, and I'll show you in a minute what all things go into this to try to make that impact. I'm basically trying to prevent problems that could lead to a high level of inspection, a high level of external failure, a high level of internal failure. Those are the things I'm trying to basically reduce by taking steps which are preventive costs. So can you think of a trade-off right now? Can you imagine a trade-off? I spend money here and the result is going to be less inspection, lower failure costs, external failure costs, and lower internal failure costs. So there's going to be a trade-off. I put some money here, I invest some money here, and the returns come by the savings that I acquire, that I basically obtain in the other things. Here's some definition. Here are some examples of what exactly I mean by internal failure, what I mean by external failures, and so on. Internal failures as listed here, they are rework, scrap, and other costs of correcting errors before they reach the customer. Then I've got external failure, which is warranty repairs, replacements, complaints, legal expenses. These are external failure costs. Then of course I've got appraisal, which is essentially inspection and tests and so on. And what about prevention costs? What kind of costs are we talking about? And these are the costs in training, redesign, inspection procedures, which are probably more effective and stuff like that. So basically what I'm doing here, I'm taking those steps that would help me reduce the first three. That's what I'm doing over here. And here's another example. Here's another way to present the same thing. I have internal failures which comprise scrap and rework. And when these decline, I have little or no defective work basically, because these are scrap and rework. And basically when they decline, I have little or no defective work. External failures, warranty cost, that's like a big cost to many companies. And product liability, these are like major components of external failure cost. And when these decline, the result is no dissatisfied customers, because they all feel pretty happy with what they get. No returns and all those things are there. Appraisal cost, a lot of money is spent in inspection. And when these decline, I require very little inspections. In fact, I'm shrinking the balloons on these three sides, internal failure, external failure, and appraisal. I'm shrinking these balloons and I'm ending up with smaller size balloons here. How do I do that? I do that by spending money on prevention. And prevention would be through process improvement, product specification changes perhaps, training costs. And what is going to increase here? The prevention, all the effort that I put into prevention. So when these increase, I end up in a win-win situation. I'm reducing losses. At the same time, I'm able to justify the use of this because there's a positive ROI, positive return on investment. Again, this is basically a repeat of what we had there, and so I won't read them again, but you can actually see that these lead to better situation. So if I raise production cost, prevention cost, if I raise prevention cost, my appraisal cost is going to come down, my external failure cost is going to come down, and my internal failure cost is also going to come down. And the result of this is there is going to be a positive return. And this is exactly the motivator for generating Six Sigma projects. Six Sigma projects look at the size of appraisal, they look at the size of external failure cost, they look at the size of internal failures cost, and they think of variety of different preventive steps that could be where money could be spent, and the result would be reduction of these with the increase here. And the net result is going to be always a positive return on this. How does the company actually save money? You might still be curious, how does the company actually save money? Well, look at the things that are the result of poor quality. And this is what you'll find if you go to a company now, one that has not gotten into this DMAC business. You'll find a lot of inspection, you'll find a lot of rework and repair, you'll find a lot of scrap, you'll find a lot of money spent in warranty services, and you have a lot of hidden costs. And I'm going to give you an example of that the moment I go to the next slide. Six Sigma exploits these costs, the ones that have been put in black color here. Six Sigma exploits them. Let me show you the hidden costs. This may be slightly hard for you to see unless you get close to the screen. What is generally visible in terms of the costs of poor quality is scrap, rework, and warranty costs. These are quite visible to people. What is not visible to them is the conversion efficiency of materials, because materials are poor quality, or they are of low cost sort of side. I tried to save some money there. Inadequate resource utilization, that also happens many times because I've got idling machines or idling labor because quality is poor, so a lot of rework is going on there. Excessive use of material, that also happens when I've got to redo the thing again, and this again is a hidden cost. It's not known many times. Cost of redesign and reinspection, this is also a hidden cost. It also stays there if quality is poor. Cost of resolving customer problems. And many times we do not write down exactly what we did in trying to help the customer, what we did, what we had to do. This is something that also is a hidden cost. Then lost customers and lost goodwill. Now this is like something for which I don't know how you can find a tag, find a money tag for this, but this is also a major hidden cost. If you lose a customer, it will probably cost you 10 times as much to bring a new customer of the same sort of value. And also if you've got poor quality, almost invariably you will have high inventory. In fact, if you go to a place where the supply materials is of poor quality, they will have all kinds of bins. These are supplies come from people, and they'll do some inspection there, and they'll sort them between good and bad, and they'll hold on to them till the dispute is resolved. The same thing happens on the shipment side also. When finished goods are put out there, a lot of sorting goes on. These are things that can be shipped immediately, and those other things, they have to be approved because there is some waiver required and so on and so forth. So if you have poor quality, you'll end up invariably with high inventory. And if you have poor quality, again, there are linkages between this and the maintenance of the machines and so on. If you have poor quality, invariably machines are going to break down also, because the culture is that way. You have your maintenance oriented culture. You have, instead of preventing problems, you probably live with the problems, and they will lead to what we have is piles of unfinished items between the different stages, and that will be like extra work in process, extra inventory and so on. The goal of Six Sigma, of course, is to reduce defects. The target plus minus, something that is far lower than customer tolerance. Customer tolerance is basically 3 sigma. What we would like to do is the process sigma here. I'm going to explain this to you in a. Let me just see if I've got a couple of slides here for that. Let me just draw a picture here. I have normal production coming out, and I'm going to be doing this on this blue sheet here. I've got normal production coming out here, and let's say my normal production, this is normal production, and that is coming this way. I'm going to first put the spec limits. So this is my lower spec limit, and this is my upper spec limit. Upper spec limit, which I found out by talking to the customer, this is lower spec limit. Again, it came from the customer. I have these two. Under normal conditions, when I am producing, at a quality level which is exactly fitting within this, my distribution of my defects quality is going to be like this. This is going to be the distribution of my defects. There are very few on this side, very few on this side. These are actually at percent level. The defects are at percent level. When I'm fitting exactly in the middle, and in fact it turns out if the standard deviation of this distribution, this is my raw production. If this is sigma, then the distance from this midpoint to this point is going to be 3 sigma. 3 sigma this way and 3 sigma this way. And I'm right in the middle. The target is right there. This is my normal production. This is not 6 sigma production. It's actually 3 sigma production, because the midpoint, the target is 3 sigma away from the nearest specification limit. This is 3 sigma production. So I'm going to tag it 3 sigma production. 3 sigma production. This is one level of quality performance. Now I bring in a process which has gone through a 6 sigma project, and the process has reduced its defects to parts per million. And there what I have a distribution that looks like this. And clearly this curve, this distribution is much tighter when compared to the other one. So let me draw this green sigma. Green sigma is here. And what I find is that the green sigma chart, it starts from this point to this point, and only up to this point is 3 sigma. And again from this side to this point is 3 sigma. And then beyond that, there's a lot of space left. If this is a 6 sigma process, then the distance from this point to the spec limit is going to be another 3 sigma, and also another 3 sigma this way. And let me explain what is going on. My new process, which is this one, which is the 6 sigma process, the midpoint of that process is 6 sigma away from the nearest specification limit. 3 sigma plus 3 sigma is 6 sigma. The distance from here for the green process is 6 sigma. And the same thing happens on this side also. I have a distance that is 6 sigma. 6 sigma, notice this is for the green process. So the green process indeed is a 6 sigma process, because from the midpoint, the average of the process and the nearest specification limit is 6 sigma away. Okay, now let's start looking at the impact of doing this. It did cost me some money to shrink a process which was initially at this stage to try to make it a 6 sigma process. In shifting a process from there to there, this change here, it did cost me some money. In fact, I shrank the process on both sides. I reduced its variability. If I did that, what exactly is the impact? Let's take a look at the impact. If you look at the tail of this, if you look at the tail of the green curve there, and if you take the tail out to the upper spec limit on this side, and if you take the tail out on this side to the upper spec limit on this side, this tail here is at parts per million level. And this tail here, the defect level there also again is parts per million. You know why? Because the curve has shrunk, the green curve. The green curve has shrunk, and the little tail of it that is left beyond the lower spec limit. There is the upper spec limit and there is the lower spec limit. This is the lower spec limit. What remains beyond the lower spec limit is going to be at parts per million. Whereas for the blue curve, it was percent. The blue curve had defect levels at percent beyond the spec limit. The green curve has it as parts per million. So what have I done? I've really reduced the fraction. I've reduced the fraction of defective parts greatly by going from 3 sigma to 6 sigma. In doing this, they may both look like sigma process, but the sigmas are different. This sigma is twice of this sigma. Look at the blue curve. Look at the blue curve, and the sigma for the blue curve is, it's like huge. And you look at the sigma of the green curve, it's half the size of this sigma. It's half the size of this sigma. This, of course, will not come free. This will require you to do some investigation. This will require you to follow the DMAC process. So how do I convert? How do I convert now my blue curve to this green curve? This conversion from here to here, this will happen by DMAC. DMAC is the framework. If you do DMAC, your old process, which is the blue curve, it will shift to the green curve. And that's a big improvement. It will cost you money. But what it will prevent is all those things that we saw: external failure, internal failure, and appraisal cost. Each of those 3 balloons would shrink because you put money now to reduce the sigma. You've reduced the sigma of the process. Sigma is the natural variability of a process. Again, I'm going to bring this up again, and I go to another occasion, and I'm going to be bringing up this thing. Let's keep moving here. So in fact, the goal here is to try to eliminate defects. That's what we are really trying to do. And the name 6 sigma refers to the variation that is within plus or minus the level that we put there. And statistically speaking, when I talk about a 6 sigma process, it is 3.4 parts per million. And conceptually, of course, what is happening? It is designed to reduce defects, and it requires obviously certain tools and techniques. And I mentioned to you that the technique that we use here is called DMAC. That is the technique that we'll be using. I will be going through the process for doing this. Six Sigma programs improve quality, and they save time, material, wasted effort, and so on. They also cut cost. And they are employed in design, they are employed in production, they are employed in service, inventory management, and even in supply chain management. Six Sigma programs are being used, and a lot of other things are there. And what does it do for management? Management provides strong leadership. This was provided by Jack Welch. Remember Jack Welch, who worked for GE? He was the boss of GE, and he did it by personal examples. We have to define performance metrics. That's something that we have to do here. We have to be much more precise than we would be otherwise. And this is very, very important. This is so important, I can't tell you how important this is. This is absolutely important. And of course, we have to select the process that is likely to succeed. If there is like a real difficulty, you can't really control the factors, there is no sense in saying that I'll be doing my Six Sigma project. There is no sense in saying that. And selecting and training people, training appropriate people who can understand statistics. And this cannot be done by shop floor people. You'll have to have engineers involved. You'll have to send them to schools, you have to send them to specialized training in statistical methods, for example. And these people, when they come back from there, they will either have a green belt or they'll have a black belt. And if they have some experience, they'll become a master black belt. These are specialized people. So you can't get something for nothing. You have to put money there, and these are preventive costs. What is the plus side? The plus side is literally companies have saved billions of dollars by doing this. There are lots and lots of documented examples, and to check them out, all you have to do is go to internet and look at the history of some of these companies. On the technical side, what do I have to do? I have to improve process performance, I have to reduce variation. These, of course, we'll have to do. I aim at reducing losses. Either I reduce variation or I reduce losses. Either way I can justify. I'll be using that by using some statistical methods, and I'll be, of course, following the DMAC procedure. This is something I'll have to do. I can't do it otherwise. What will the team comprise? Top management will be obviously directly involved. There will be program champions. These are people who have a big stake involved in the success of the process. You'll have master black belts. These are the guys who are really the dadas. They are the honchos. They really know what is going on. They understand process. They also understand statistics. Then you got black belt people. These are dedicated people. Their hands are dirty always. And they are into the process. They are fixing things. They are guiding people and doing all those things. Green belt people know the statistical methods, and they can help along as the process is going on. They can help along in data collection, planning the trials, and all those things. Green belts come very, very handy. They know also plenty of statistics. So what is the DMAC procedure? It is define the problem, measure the quality characteristic that you are looking at, that you want to improve, analyze the situation, perhaps use some TQM tools if it is necessary, and don't forget the cause and effect diagram, because eventually you want to run some trials, some experiments in a structured manner, and that can happen only when you've got the factors identified, and the factors can be identified only when you've got your fishbone diagram done. Then of course you'll be doing improvement, and improvement would require you to do some experiments. I'll show you a little example of that. Once these things are standardized, then you do control. You put in SPC in place and you start controlling the process. That's something you'll do. Parts per million, how do I measure that? You look at the opportunities. How many opportunities are there to make a mistake? And what is the actual mistake that happens that really remains in the system after I've done my Six Sigma? So look at the number of defects that remain divided by the number of opportunities for error per unit. A unit could be some object where probably there is a chance of an error happening. You look at that object, you try to find out, oh, there are so many circuits. That actually means there are so many opportunities of a mistake, so that you put down here number of opportunities multiplied by number of such units that you produce per day. That will give you the total number of opportunities where you could make a mistake. Then you look at the actual number of defects that you produce, multiply that by 1,000,000. You'll end up with the defects per million opportunities. That's actually the metric that is used in doing Six Sigma. So define, that is the first step. And what do you define? Who is your customer and what is their priorities? And what are the quality characteristics they are looking at? You'll measure the process and its performance. You'll analyze using causes of defects. You'll bring in your cause and effect diagram, identify factors with which you'll be doing some trials. Then you'll be doing the the improvement experiments. And your effort here is going to be to try to remove the causes of the defects. That's what would be the thing. So you have to optimize the process factors. Then of course, once that is there, you know the optimum conditions, you know the optimum parameters, optimum values of the parameters. You basically have to maintain that quality. Once you're maintaining the quality, of course, you're operating at the Six Sigma level. And that's exactly where you want to be. So you start at D, then you go to M, then you go to A, then you go to I, then you go to C. You cannot jump these steps. I have tried to jump the steps and I had egg on my face. In other words, I was a failure. The project was a failure. If you follow this process, if you follow this DMAC process, you're going to be, you'll have a much higher chance to succeed. That is something there. Roles and responsibilities, management really, you can't throw away management. You can't say all this will be done on the shop floor or by a couple of engineers. You just can't do it. And this is where TQM tends to go somewhat behind. TQM falls behind, the Six Sigma goes way behind TQM, way beyond TQM. That is something that happens once you get into the Six Sigma mode. What other tools are used? There's certain things called opportunity flow diagram, and I'm going to be giving you some details in the later lectures. I'll be doing that. You do FMEA and you obviously do DOE, design of experiments, and I'm going to give you a glimpse of that in this lecture itself. Quality improvement is like one of the missions, and reduction of variance or reduction of variability, that's going to be one of the objects. And if you remember the slide that I had here, I started with a process which was the blue process. I had the blue process, that is the initial process. So I did my D and M and I found my process was at this stage. Then I did my analysis. What did I do with my analysis? I took this process and I tried to construct the cause and effect diagram. So I took this process and I constructed cause and effect diagram. This is what I did with this process. And I located the various things that could be going wrong. And that is like this thing. I have factor A, factor B, factor C, factor D, and probably some noise factors also. Those are there. And my response is here. Response or Y or quality characteristic that is there. Basically, that is the output that I would like to see. When I'm constructing this, I'm in the analysis phase of DMAC. Once I've identified the factors that I'll be playing with, I'll be moving to I, and I'll be planning design of experiments. So here what I've done, I basically tried to reduce variability. Initial variability was the blue sigma, which was high, and I brought it down to green sigma, which is a smaller, which is a tighter process. It's got a higher precision. So here I've reduced variability. Here I've reduced variability. I've taken it from here to this level. And there is another approach to try to apply your Six Sigma logic. You look after waste reduction. Try to find out where your waste is and you try to reduce that. And the Japanese call it Muda. Muda is waste reduction. And basically this is also another approach or another strategy that you could utilize when you're doing Six Sigma. You could do that quite easily. Let's take a look at DOE. I'm just going to give you a glimpse of DOE, and you'll actually see, you'll end up seeing how useful this particular tool is in locating the sources of problems. Let's start with this little diagram here. And if you're sitting in front of me, I would probably ask you a question. And let me ask you the question anyhow. On the right hand side of this diagram, I have my digital watch. You see my digital watch here? I'm showing you my digital watch. I have this digital watch sitting at the right hand side of this diagram. This is the digital watch. And on the left hand side, I've got other types of systems. I've got the weather, the monsoon weather, for example. Or I could, talk about other things that are unpredictable. I have the economy, and no one really knows where today's economy is going. This is the middle of 2009, and we really have no idea which way the economy is going to go. And then you look at slightly more, perhaps more understood systems, but still pretty mysterious systems, called this whole body of psychology, human psychology. That is like another area. So look at the two extremes. On this side, I've got electronic watch. On this side, I've got nebulous systems like the weather, for example, or the economy or psychology, for example. Now, can you tell me, can you actually think of the difference between systems on this side and the systems on this side? Can you think of the differences? Think for a minute. You'll probably say, well, Professor, on this side, as far as electronics is concerned, I can write all the equations that go into making that digital watch. I can write the exact equations. And I can fabricate that thing with the methods that we have now to a nanosecond. I can correct the thing. I can make sure that this watch operates within a nanosecond of thing, certainly for a day. And in a year, maybe it'll lose maybe 2-3 seconds, that's all. I've got such perfect understanding of the system on this side, on the electronic side, that I really have no issue, no problem at all on this side. My knowledge is pretty close to being perfect on the right hand side, which is toward the digital watch. But my knowledge on this side is very nebulous. I hardly know anything about how the weather gets affected by maybe the flutter of a butterfly or a waterfall somewhere or God knows what. The way the wind is blowing and the effect of greenhouse gases and so on. I do not really know what affects the weather. I do not completely understand that. Very few people actually do. In between we have a whole range of systems. For example, we got medicine, you understand somewhat. We got chemistry, then we got engineering, mechanical engineering and so on. These systems are such, they are better understood than these systems on the left hand side. But these systems are not as well understood as electronics. I do not really have good equations in medicine or chemistry. We have some equations. And in fact, how are those equations formed? Sometimes, of course, you got pure theory, like Ohm's law, Kirchhoff's law, Newton's law, and so on. And those could lead to some degree, they could lead to design of systems based on basic theory. And those are the product of a lot of basic research. And they have produced that body of knowledge. And we can utilize those equations then to design systems which are near perfect, for example. In between, we have a lot of things for which we have no equations today. And there, the technique is empirical, run experiments. In fact, in many cases, we normally run only one factor at a time experiment. So in chemistry, I have a sister, and she's a top-notch chemist. She works in a top-notch university, but when I talk to her, she always talks in terms of the effect of one parameter. She says, if I use this catalyst, the reaction runs faster. Then she shuts up, and then she, again after 10 minutes, she says, when I change temperature, the reaction gets slower. It becomes slower. Then again, she shuts up for a while, then she comes back again after she finishes tea. She says, you know, when I change the concentration of something, some component that goes into this reaction, I see a precipitate forming. All the time she is talking about one factor at a time experiments. Unfortunately, in real life, if you look at a cause and effect diagram, and I'm going to show you again the one which is right here, and I'm going to shift the paper a little bit so you can see the full cause and effect diagram. Now you can see the full diagram. These are the factors that are affecting this blue process. Somehow I have to take this blue process to this green process. I have to convert it. I have to make it the green process. And I have found out by talking to people and doing brainstorming that there are these 4 factors, A, B, C and D. They can all influence Y. I cannot do one factor at a time experiments here. Because there is a phenomenon called interaction. The effect of A and the effect of B, they may interact. In fact, it's very possible the effect of A, C and D, they interact in a very complex way. So if I had to optimize Y, if I had to maximize Y, or if I had to minimize sigma, sigma is something I'd like to minimize. I'd like to take this blue sigma, I'd like to convert it to a small sigma, the green sigma. This is what I'd like to do. I know that when there are so many factors, there could be an interaction also going on, and that might be affecting the process. So in this case, unlike what my sister does, I cannot do one factor at a time experiment. I cannot have any kind of success by running one factor at a time experiment. I'll have to run what we call multi-factor experiments. So 2 or 3 or 4 factors, they'll have to be run together. And this will be done using a matrix type of structure. I'll give you a glimpse of that. I'll just give you a glimpse of that right now, because I'm not really running through a full lecture on DOE. But this is DOE. DOE is design of experiments involving multiple factors. Design of experiments involving multiple factors. That's what we are trying to do. And those would be useful right in the middle. Right in the middle, when we've got medicine, chemistry, engineering and so on, we will be using these multi-factor DOE. So in fact, on top of this, you could write DOE. DOE is the way to take these systems from the left to right. Now, can you do DOE with weather? Can you do DOE with psychology? Can you do DOE with economy? First of all, these are large systems, very complex systems. The second factor is, many times you cannot draw the cause and effect diagram when it comes to economy. You cannot draw the cause and effect diagram. Our knowledge has not progressed to the point when we can write down all the different factors that affect economy or inflation or whatever. We're not able to do that. And because of that, what we have to do is we have to really restrict the application of DOE to those systems where I can draw the cause and effect diagram. Unless I'm able to do this, I cannot do DOE. I cannot really hope to get to Six Sigma. I just cannot do it. There's a limitation, that is a kind of a block there, and I cannot really go through the block and reach a Six Sigma level without having done this work, which is like construction of the cause and effect diagram. How will I run my experiment? Where will I find the factors? Which factors will I play with? Which factors I'm going to set at low level? Which ones I'm going to set at a high level? Unless I'm able to do that, I'm going to be a complete failure. So let's see how this is done. We start again with a system that has got multiple factors. Now, sometimes what happens, you might be able to observe the correlation between two factors, and I've got two factors here. If you look carefully at the screen, I've got walking speed and I've got heart rate. Now, we all know, we are human beings, we know as we walk faster, our heart rate goes up, and there is a correlation here. What this is really trying to say is, if I want to control my heart rate, I can do that by adjusting my walking speed. This is kind of a cause and effect relationship. This is what this is. And this relationship here, it's a very crude one, but this correlation plot here, this scatter plot here, it gives us an idea. There is some hope here of controlling heart rate by playing with walking speed, that I could do that. This is a one factor at a time experiment. Imagine now, if you've got 2 or 3 different factors, they all have effect like this. How do I find out what is affecting what? How do I find that out? I'm going to show you how. I'm going to take an example, I'm going to show you how. So think of the real system which has got a lot of variations, lot of sources of variations. So if we did the cause and effect diagram, it will be pretty complicated. It will be sort of like this. And the cause and effect diagram itself will be pretty complicated. It will be like this. And then of course you'll have to see, can I boil them down to 3 or 4 factors or 5 factors? And then probably there is a chance for me to do some experiments. Let's see how we do that. What is the logic for doing the experiment? I have my cause and effect diagram, which is this one. From that, I select factors. I select factors based on experience. And what is that experience? People tell us, people who are knowledgeable about the system, they say, well, sir, in this case, if you're looking at a response, power outage is important, and burned out bulb is important, and not plugged in plug is important, and switch missing is important. These are 4 important factors. So why don't you do experiments using this? Here I'm using a person's experience who's got some experience with this. But still, he's not able to give me the precise answer that I'll be able to find with the help of DOE. And I'm going to move in that direction. So I'll start with his knowledge base, which is now put in the form of this construction, this cause and effect diagram. What I then do is, I try to sort of say he's given me 3 factors. I have to run now multi-factor experiment, and listen to this very carefully. How many factors are there? You can actually see I've listed out factor A, that's one of the factors, factor B is another factor, factor C is another factor. And imagine these three factors together, they are basically driving the process. They are running the process. So I have a cause and effect diagram here which has got factor A driving it, factor B driving it, and factor C driving it. What we do not know, which of these factors is really the culprit, which of these factors is really the important one. And indeed also if there is an interaction between factor A and factor C, if there is an interaction, that also is something that we'll have to discover, because we want to optimize the process. We want to control the response in a manner that will reduce the overall defect in the process. That's what we would like to be able to do. Let's see how we do that. The first question that we have to resolve, we don't jump at optimization. Like we don't get our PhD right away. As soon as we enter IIT, we don't look for the PhD degree. We do our BTech, and within BTech we do first year, second year, third year, fourth year. Then we go through another test and then enter our MTech, and we do first year, second year of MTech. Then we move on to PhD, and PhD again we've got an entrance, we've got 1 year, 2 years, 3 years. Maybe in 3 years I'll complete my PhD. So I've went through stages. And what I have to remember is, in doing experiments also, I do not quite jump to the optimized state completely. First I get my first year of BTech done, then I do my second year of BTech and so on and so forth. Then I reach a certain level, then I see what else can I do now. Or I could do probably a few more courses and so on. I could do a project, then I'll be ready for my PhD. Then I can start my PhD. So let's see how we do that when we do a Six Sigma project. The first question that I ask is, does factor A have an impact? That's all. Does factor A have an impact on my process? Does factor B have an impact on my process? And does factor C have an impact on my process? If I ask this question of my sister, she would just say, oh, there is no problem at all, bhaiya. What you do is, you run a trial using factor A, only factor A, and just see if the curve kind of goes up. That means factor A has an effect. And then you clean up the table and so on, put everything away. Then you bring in factor B. You bring in a catalyst. And you put the catalyst a little bit, then a little bit more, and so on. And you try to see what happens to the process. So you got a response based on addition of factor B. Then you put that aside and you bring in factor C. You do the same thing. So you have a response that was generated by factor A, a response that was generated by factor B, another response that was generated by factor C. I said, good, sounds good to me, but it does not give me the answer, because in the real process I have A changing, B changing and C changing all together. Can you tell me how I can find the composite effect of A changing, B changing, C changing? My sister says, you're asking a very complicated question. I don't think this can be done, because I'm not seen in any chemistry paper or physics paper people manipulating 2 or 3 things together. This is, I don't think such a question is a relevant question. I say, but you don't know. I'm trying to improve this device, and things that can actually change with this is the battery voltage, something about the screen, and something about the software that is there. 3 factors. And they are all interacting perhaps. So the performance of the total system now is dependent on factor A, factor B and factor C. That is the total, that is what determines the total performance. How do I take care of this? And for this there was a method given, and that is called a matrix experiment. And I'm showing that matrix experiment on the screen here. Let's take a look at it. It does look like a matrix, does it not? It looks like a box. But look at it a little bit more carefully. I have decided to use only 2 levels. Only 2 levels of A. I've decided that I'll set A, I'll run my trials with A set only at 2 levels, a low level and a high level, that's all. And then of course, I have factor B, again I've decided I'll try it only at running at low level and running at high level. And then I've got factor C, this guy, he's also at 2 level, factor C at low level and factor C at high level. Now I've got 2 times 2 times 2. What is the total number? 2 times 2 times 2, that is 8. So I've got 8 combinations of low and highs. Are you with me so far? I have factor A, which can be set at 2 level. So I can run 2 trials with factor A at low level, factor A at high level. For each of these trials, I can set B now at low level, high level. So I can have A set at low level and I can run B at low level and high level. And then I can move A to high level and I can run B at low level and high level. That also I can do. You can see that. This is factor B and this is factor A. So factor A at high level, then factor B could be run at low level and factor B could also be run at high level when A is being held at high level. Take a look at the matrix. Take a look at the matrix that I have here, the box. A can be set at low level or it could be set at high level. And while I am changing this, I can change the setting of B from low to high. I could do that. As B goes up, it goes from low to high. And then of course I've got a combination of A and B. So this box, this square here, it shows me the low combination of A and B, the high-low combination of A and B, the low-high combination of A and B, and the high and high combination of A and B. And these 4 settings, they were done with C set at low level. These are my 4 trials. And then I've got similarly, I've got 4 trials at C at high level. And those are the back walls. So I've got a total of 8 different possible trials. Great. I've got 8 trials now. I will be running my experiments at each of these blocks, each of these balls. Each of these balls basically they show us the different experiments I'll be running. So I've run here 8 trials with the low and high combination of the 3 factors. Then I do something called data analysis. After I've done this, and this I'm going to teach you later on, I do data analysis. The result of data analysis is I have observations here, and so on and so forth. I have all these observations. What I'm really after is finding something called main effects. Main effects are the effect of factor A and the effect of factor B and the effect of factor C independent of the effect of any other factor. Let me repeat again what I said. By doing these trials, these 8 trials, and by doing my special data analysis, which I'm going to teach you, I can isolate the effect of factor, the effect of changing factor, setting of factor A from low to high. I can find that effect. I'm going to show you that in a minute. The same calculations can also show me the effect of going from B set at low level and then set at high level. The impact on response when I change my setting of B from low to high. I'll be able to see that effect also. And the same thing I could do for factor C. Whatever is the effect on the response of the process, when I shift the setting of C from low to high, whatever the response is, whatever the impact is on the response of the process, that also I can observe. And let me show you where those are showing. Look at the curves plotted. Look at the curves plotted here. These curves show you when I change the setting of A from low to high, the response goes up. Maybe going up is good. So response improves when I raise the setting of A from low to high. With B, the effect is exactly the opposite. I bring down the response. Response actually gets worse when I change the setting of B from low to high. And when I do the same thing for C, I again find the setting of shifting the setting of C from low to high reduces the response. Now, just by looking at these things, which factor will you say has the highest effect on the response? Which factor will you say? Is it A, or is it B, or is it C? Well, it's pretty obvious. Factor C has the highest effect. Factor C has the highest effect. Now that was just main effect. There is a similar possibility, there is a similar procedure available for me to find out whether factor A or B or C, whether they interact with each other. And also if their effect is significant. And let me tell you a little bit about this significant business. Say in this room there is hardly any noise, so you can hear my sound. But actually you may not know this, there is a very faint noise in this room, which is the motor that is running here inside the PC. And suppose my signal is reduced, my signal is my voice. Suppose it is reduced to the level when my signal and the noise coming out of the PC, they are at the same level, and let me try to do that. Can you hear, could you hear anything? I doubt if you could hear anything at all. Because my signal, which is my voice, had come down, I had reduced it to the level when basically it was at the same level as the background noise. At that point, you'd probably say, sir, you're quiet, you're not saying anything. In fact, the same thing we do when it comes to testing the effect of these factors. We say that the effect is strong if the effect is audible, audible in comparison to the background noise. If that happens, we say the factor has an effect. If that does not happen, we say the factor has no significant effect. That would be one stage. When I move from there, after finding these effects, I can go into what we call a mathematical equation, which is a predictive model. And here I put response on this side, I've got my ABC factor here. And then of course I have constructed a model. This model can be very handy in optimizing the process. So that would be the next goal. So I did my experiment, I found the factor effects, I did my plotting, then I constructed this mathematical model. The last stage is you either reduce variation, which is like when you reduce sigma, you reduce this sigma from being blue to green. This you do by doing your experiments. And or the other thing is you could also directly reduce defects. That also is something we could do. There I am optimizing the process. Once I have found the right settings for A, B and C, then I can do control. I can actually bring this whole thing into what we call the control mode, and I can put SPC to monitor the system to make sure it stays there. Let me show you what happened in a real application. The Nissan company, it found suddenly that the Nissan logo was falling off the cars. On the back of the car, they used to paste this logo. When the car was ready, finishing was done, painting was done, everything was okay, polish was done. Then they took this logo, which was a nice little thing that said Nissan, and they stuck it with some glue, they stuck it on the back of the car. But the customers complained by saying, these logos keep falling off, and we have to come to the dealer again, get another logo, which is not so good. And this is a big problem there. And this turned out to be a few percent of the cars, maybe 10-15% they were losing their logos. So this was an issue. So the definition of the problem D was, there was a problem with this thing. They measured it, they found about 15% logos were falling off. Then they started doing the analysis. And they constructed the cause and effect diagram, which I showed you on the tree again. I showed you the cause and effect diagram, which is this one. They constructed the diagram, and in doing that, what they found was there were these factors that could be affecting it. Addition area, that could be one factor. The other factor could be the type of glue that was used. The third factor could be the foam that was used, the type of foam that was used, and the thickness of the logo. And then there were some other factors also. The amount of pressure that was applied to stick the logo to the wall, that also was something that could be done. So this is something they started to play with. They constructed a matrix, and let me show you the matrix. Here's the matrix, here's the experimental matrix. You see factors A, B, C, D written up there. This is the logo, this is the experiment actually, and the experiment actually was done only at two levels. High level, which is shown by a plus, and a low level that was shown by a minus. And you can read the matrix there, and you can actually see the first trial. This was a matrix experiment. Just like we had 8 trials there, we also have 8 trials here. The first trial produced a gluing strength when A was set at high level, B was set at high level, C was set at high level, and D was at low level. Glue strength turned out to be 9.8. Then they changed the setting of A in the next trial, plus, that is high, high, low and low, and glue strength turned out to be 8.9. This had to be measured because this was the response of the system. So they ran all these 8 trials. Having done that, they found the factor effects. And I'm going to show you the plot of the factor effects. The plots are this. You can see the factor effects there. You can see the plots. This is very similar to what we've done before. If you think of it now, this is very similar to the kind of plots that we had before. Now we have this plot. And of course, these red circles, they are showing you the best setting for factor A, the best setting for factor B, the best setting for factor C, and the best setting for factor D. And these are real factors. They are like your process factor: addition area, then the type of glue used, thickness of the foam, and the thickness of the logo. And it's very easy for me to see that this is exactly what this is. This is how I optimize the process. This is how I end up optimizing the process. So the goal is to reach the target and to make sure we have basically no red lines, no red areas. This is something we'd like to be able to do. That is really the effort. In more complex processes, the response surface may look like this. In this case, you'll need to run more complex experiments, but it can still be done, and that has been the approach in statistics. And of course, the Six Sigma people, they use many other techniques. Everybody can use these 7 tools. Most people, they can plot the control charts, but the design of experiments and modeling and optimization, those are done generally by black belt people. They are the guys who can do those things. And the black belt, of course, is the leader, and so on and so forth. So if you read the next of the slides, next lectures, you'll be able to see that. And I have a slide here right at the end of the talk that describes basically the different stages of your understanding of the process. Take a look at that. I tell you about the state of knowledge, which could go from 0 to 8, their description, what it actually means. How will you manage production if your level of knowledge is right stuck at 2 or 3 level or somewhere there? What quality improvement strategies you'll be using, and what are the relevant tools, Notice here, I do not use SPC or DOE right at the beginning. I don't do that. I wait till I reach a certain level of understanding my process, which could be level 4 or level 3 or something. Only then I bring in SPC and DOE. Of course, when I reach the last stage, my performance is like my digital watch, which is an automated system. Thank you very much. We'll follow up in the next lecture. Thank you.